me? Okay, thanks everyone for joining. And today we have the pleasure to have Professor Ruoming Jin from Kent University to give a talk. So a brief intro of Professor Ruoming Jin. He is a full professor in the Department of Computer Science at Kent State University. His research area include artificial intelligence, deep learning, recommendation systems, big data, graph database, and health informatics. He has published over 150 research papers in these areas. Most of them are in the top venues, such as KDD, ICML, NeurIPS, SIGMOD, PVLDB. He served as numerous program committee members for these conferences. And last year, he served as the TPC co-chair for the 10th International Conference on Computational Data and Social Networks. He has also filed and awarded several patents and received over $6 million in research funds as PI or co-PI. He's also the recipient of the prestigious NSF Career Award. He also co-founded GraphSQL and Tiger Graph and served as its founding CTO for the last 4 years. And again, it's our pleasure to have Professor Jin with us today. And Professor Jin, the floor is yours.
Okay, thank you. Thanks for the introduction. Yeah, thanks for the invitation. It's really a pleasure to give a talk, just introduce some of our recent work on recommendation system. So before I start, I want to kind of motivate our study a little bit. So really, like for the last probably 2.5 years, I would say, like less than 3 years, we have been looking at the recommendation system, recommendation models. So basically, a paper sort of coincides when we look at this field very carefully. It's this paper. I don't know. I would strongly recommend everyone to read it. This is the Rex's best paper 2019. So the paper really like just showing a lot of deep learning models at that time. This is about 2 years ago, right? There's tons of new deep learning models for recommendation was developed. However, when they were, and most of those algorithms are in the top venues. So when they look more carefully into those papers, and they did, just a standard, I guess it's the experimentation, right? Comparing them with the, sort of classical linear or even simpler nearest neighbor based approach, and they found actually most of the results are not as claimed as they are. So basically, it's sort of a mystery, right? Like the deep learning models, as claimed they should work better, but they really doesn't in many cases. So this is, when we found this paper, like I guess it's slightly in the fall of 2019, we actually have our own experience as well. My student and some of people I work with, we have been experimenting a lot of, the state-of-the-art deep learning algorithm at that point. So probably even 20 or 30 different deep learning algorithms. And our results also very much coincides on or in agree with their discovery. Yeah, like at that point, I was really scratching my head. It's kind of like, what's happening, right? Like all the algorithm was claimed they work better, but when we run it on some standard data set and also some preparatory e-commerce data set, most of them do not perform better than even the standard ALS algorithm. So it's I always assume there is something wrong with the implementation. We have tried different various implementations by our own and by others, but none of them really success in improving some of the standard benchmark. So this paper sort of really sheds the light the way they were working on that, and that really also drive us to consider what are the really take a deeper look of how should we approach recommendation system, right? So there is many different, to lead this discovery, right? To lead a lot of, I guess it's a little bit false discovery over the years. It's really on one side, we feel, it's clearly on the evaluation metric. That's also what the paper addressed. Sometimes people pick up some non-standard, evaluation matrix, which can lead to false discovery. This is, I will talk a little bit more on the second part of the talk, which is how we get started, like particularly how the sampling-based metric, like if you do an item sampling for your recommendation algorithm, then you have to be really careful. But in the same time, we also want to use the item sampling. So like what type of approach can help us recover the global global evaluation metric. So that work, one of the discovery made by two researchers, Randall and the other researchers from Google, actually won the 2020 best paper in from KDD. In the same year, we published a paper in the same venue just to show there is a way actually you can explain the sampling based recommendation results. Okay, but this is just an area which hasn't been touched, this topic. So on the other topic, we really look into basically say, instead of the experimental comparison, right? Can we have a better understanding of different deep learning and linear models? So we try to get an understanding of why they perform as they do, and so can we put them in this understanding, because typically in the recommendation community, we always do that through experimentation, right? There's not much theoretical analysis of the different algorithms because it's hard, right? Like you consider even an ARS algorithm, just because we run a very complicated, even alternating least square or gradient descent. So all of this is, we don't know what the solution look like, how we can theoretically compare them. Okay, so that's how we, last year we have, one KDD paper, 2021 is actually take one step back. We develop approach using closed form formula, okay, to approximate actually of those sophisticated recommendation algorithms and to show why different, scenarios, like, a particular case is, the linear regression based methods actually, why they can perform better, or at least give a theoretical framework for you to compare different algorithms, okay, under the same umbrella, okay. Yeah, so this is sort of, how we kind of, how we started, what motivate our study. So we are not in here to introduce any new algorithm, okay? But we really look at the foundation of the recommendation models or the recommendation evaluation, okay? We try to help, to make it, I guess, is more with a more solid foundation. Yeah. And so one thing is, like, if, in case you have any questions, feel free to, stop me anytime, okay? You raise your hand or you can just, yeah, because I guess it's, like the presentation is a little bit, formula intensive, okay? So, yeah, if you have any question, please feel to stop me, okay? All right, so let's start with the first talk, right? The first part of the talk. The first part of the talk, I'm going to look into different recommendation models, particularly the linear models. So how they were really connecting to one another. And the study focused on implicit, recommendation setting. So I guess it's most of you, I assume, are fairly familiar with. The implicit, I think, is also interesting. It's in Netflix context, but the implicit, in most of the e-commerce setting, that's kind of, how we approach the problem, right? So basically, we are trying to providing a list of recommendation for a user. Then our input is really it's a binary matrix for this way, right? So you are each row corresponding to a user. This is the user may have, if it's interactive with certain items, either click or add cart, then we have the symbol yeah, we have them annotate to be 1. If it's no interaction, whatever, we keep them at 0. So each column is corresponding to an item. So this is basically for each item, we have all the, for all the users, whoever interact with the item. Okay, so this is the starting point, right? Then, yeah, like so yeah, like this, whoever, what this symbol just to say, like this set of the items for this user was in this positive side because they have interactions. The rest does not. Yeah, our goal is really just trying to predict. So we want, like for the standard, recommendation setting, we can, I think in the weaker case, we can just hide certain ones, right? Then then train them, then to see whether we can recover the ones. Then in the stronger case, we could hide a list of users, right? So we train the model, then in the testing, we will also, for even for the testing case, we will, for that testing users, we will remove some ones, right? Then to see whether we can recover them in the top case. Then, basically the recommendation, largely speaking, if we eliminate all the totally heuristic approach, it can be largely classified into these 3 categories. Matrix factorization based approach or latent factor approach, the regression based, neighborhood approach. I will explain a little bit more of that if you are not familiar with that. Then finally, the deep learning based approach. Okay. So basically, yeah, like you can, sort of like, because our goal is to kind of understand them, right? Those different models. So I have to put some, like a mathematical formula, but if you work on this, it's easier to understand. Really, like for matrix factorization, we just want to have P and Q, and then we have certain regularizations. Then for neighborhood approach, you can think of it really like we use X is our original, data. Then we are trying to learn a W, okay, a matrix W. Then we have a regularization for W. So this is, generally speaking, this W is full ranked solution. But in our study, we actually look into also low rank regression. So this is very similar to linear autoencoders. So you have this A and B. So W can be decomposed into A and B. Okay, then we will regularize AB in a certain sense. Yeah. Then deep learning, basically we have this neural network. We get X, but we will try to see whether we can sort of recover X. So there's many different ways of doing deep learning. Yeah. Okay. Yep. So last year when we start, early last year when we look at this problem, we specifically started on asking this question, right? So on one side we know the matrix factorization approach has been very popular in the past and also widely used in industry. I think there's a standard library in all the open source repository or like Spark or the different big data system. You can even call them get it almost free, right? So they were also like getting reasonable results. But in the last few years, this we call the linear regression based approach is sort of model based neighborhood approach seems actually perform better, at least in the offline metric. So and in the study of the 2019 paper, particularly Yeast or Slim, they'll getting competitive results even against the sophisticated deep learning models. Yeah, they are very competitive. So sometimes even perform better, right? So and also like the regression-based approach, when comparing with matrix factorization, seems definitely have an edge. Okay, so yeah, like really, so the first question we ask is, okay, so what's going on? I mean, both of them are like very simple linear models, in a certain sense, right? And the matrix factorization in some sense even looks like more general, right? So this is, look at the matrix factorization, right? Because you have a matrix P and you have a matrix Q, then, really we try to get in, like think about for P matrix is a user matrix. Every user, we have a latent factor. Then every item we have a latent factor. Then, like if we do the estimation, we really take the user multiple by the corresponding item vector, right? Then we getting our estimate. And like in the most famous, like ALS algorithm, right? The 2008 like ICDM paper, right? Or called weighted matrix factorization. You even have a C matrix here, which you can adjust the weight for different cell. So this is quite a powerful setting, right? You have one thing you can say, oh, this is my parameter space are pretty large, right? So if you have, let's say K, 100 dimensions, that means every user, has 100 parameters. Every, item has 100 dimension vectors. So that's a pretty large, like a parameter space. Then, we do the standard is you do a, L2, or Frobenius norm regularization. And then the standard solution for this, right, is, we call alternating least square. Really, you fix one of them. You fix one of the P matrix, then the other, it's a sort of standard, like, ridge regression. Or yeah, like then you fix Q, you do the other. So you can do this regression iteratively, or least square iteratively until, it converge. So it's a, yeah, this is very simple, very powerful, like algorithm. That's, one of the, and also SVD++, this is for explicit setting, right? This is like award-winning algorithm as well. Those two are really like, I think this is from before the deep learning, right? This is definitely the best algorithm out there for recommendation algorithm. We, sort of like become the de facto criteria of what's recommendation about. Yeah. Then, so the, okay, let's see if I have any questions. Okay. Yeah, sorry, like, can you guys see the question? Yeah, like I think some of them talk about, the matrix is very sparse. I think, most of matrix are actually very sparse. As we will see, like when I talk about the closed form solution, it doesn't, like really matter. I guess it's, like if your matrix is sparse, the industry standard solution is actually, introduce more. You can use features, right? You can use features of, items, for instance, or even, feature of users. So you can adding additional features would help with some of your recommendation. Yeah, and also like you can even use we call impression data. So like when the user start looking things, those signals are actually what item they have been looking at. That's also very important. So there's I think the impression data, how it was used in recommendation system hasn't been like thoroughly studied, but that's one way, we have been looking at. It's getting some interesting results. So that's something you can look into. Yeah. So yeah, I will explain W for a second. Yeah. Yeah. Yeah, the one of the question is whether, the linear regression based approach is relate to graph neural network. Yeah, in some sense it's sort of, but graph, depends on how we look at graph. If there is actually research talk about using more like a binary. You can do like kind of graph neural network over binary network. So you have user, you have items. So in that setting, how you do the how you do the like a regression or like a graph neural network. Yeah. So yeah, there's probably the last 2 years, there's quite a bit of work, but frankly, I'm, kind of, we haven't, compared with them really, but I'm a little bit suspicious of, like how effective the results would be. just comparing with the like EASE or EDLAE. Okay, so let's look at what is W, right? So think about you have this X, right? This is your like your data, right? Like for each user, how many items you have been look at this. Then this W sort of you can consider it's really almost like an influence matrix. So basically it describes how one item is going to affecting another item, right? So it's really like if you close, let's say, a cell phone, maybe how it's related, like how much it would contribute to an ice cream, right? So this is like more like if you are familiar with the neighborhood approach, which I assume most of you are, this is sort of just more rigorous way to solve the question, right? So in the regression, in the typical neighborhood approach, how you do, right? In item-based approach. So for this user, assume you click those items, right? Then if you want to do a prediction, you are just going to calculate there is a calculated score going to say, oh, how this particular item is related to the other item. Okay, I mean, that is the similarity measure, right? You define, you can use Pearson correlation, cosine metric to see how, each item is related to another item. And then you can sort of using that similarity to transfer your score from the original item to other item, right? Then you aggregate. If this particular item, you can, like in this case, you have this two item, you can get in two of their influence, then added them together to get into prediction. Okay. So yeah, like in our, like if you think about the matrix, right? For this user, if you have this X, right, you multiple by another, like by a targeted column, like this column, right? So this is really just, you can think of this as each row is a source, then the column is really your destination, right? You will see, for different, if you have, the cell phone and ice cream, right? Like how likely you are going to, you will getting a T-shirt for this user. Okay, then. So really like this regression-based approach, I think the first paper is from Slim 2013 or 12. This is from the Minnesota group. Really like they introduced a rather sophisticated, regularization. Have this, L1, then this L2. They also say, oh, this W because this is, influence. They will make sure this is a positive matrix. Then the diagonal, one of the major things actually really play an important role for matrix, for this regression-based approach. They will ensure the diagonal is 0. Okay, so basically, that means if you already click item, that influences, you don't want to, kind of yourself would contribute to that item at all. Okay, so that is actually can help always boost the efficiency, the accuracy. Okay, so the diagonal is 0. So in this case, this is quite sophisticated. So this is really, you have to use, gradient descent or some other, methods to solve this this problem. Okay, so but it's like iterative optimization. Okay, so I think in a way like a breakthrough is, this is from the EASE. I think this is from 2018. So really like the author, I think it's Stack from, like Netflix. So he really simplified this model, right? He said, okay, let's drop this L1, let's make it drop this positive. So I just have this diagonal to be 0 constraints. And by doing that, he's able to actually find a closed form solution, okay, in this problem. Okay. And the other thing quite remarkable is think about this problem. This is almost, I think, the first time a closed form solution shown to can actually work on the real problem. So it's like one line of code. Its performance is better than all the things people have done before. A lot of things people have done before, like including the matrix factorization. Okay. And this W, by the way, is a full rank in this case. This is like if you have n items, so this n times n. Okay. Oh, yeah. So yeah, one of the question, this is yeah, like I think it's partial. Yeah, this is partially, we make diagonal to be 0, like if it's the same item. So we don't want to take that into consideration. I think what happens is, this is purely from the performance perspective. Like if you already, because anything we do, you can think of when you're doing the inference, right? When you're doing inference, you never have the item. You typically you would remove that item. You won't say this item I have to do recommendation again. So if you consider, you have an item, then I want to recommend the item again because this person will likely to buy. By the way, in the real world, we can see actually people like repeated purchase. Okay, but in that case, this is the temporal setting would get involved, right? So you can you have to have time dimension into that to make this type of recommendation to be more effective. But in our problem right now, like I think this is more like the academic setting or like the standard recommendation setting. We are eliminating the temporal factor, right? So in that case, any of our training, the testing scenario is by eliminating that, make the model much more efficient. Yeah. Okay, so then in 2020, this is in 2020, I believe, NIPS. So, he moved this forward, adding one more constraints into, so basically instead of using this lambda, it's using a capital lambda. So this is corresponding to adding a dropout, but then, this is the unexpectation. This is kind of linear dropout regularization. And he was able to show actually, again, this is, if W is full rank, then it can has a closed form solution, very neat formula. Okay. But all of this is all full rank, right? So W is pretty big, right? So this is quite different. You can see this is related to the page rank, but you can see both are linear models, but they also differentiate quite differently, right? Like so how we can even study them under the same umbrella. So we have to kind of, this is how we like yeah, how of the problem we are tackling in our last year's KDD paper. So what we are seeing is, okay, let me see if we close this. Yeah. Yeah, like this is your, based on this, you can get your, recommendation results. Yeah, this is, I already explained. So, so instead, we are seeing is, because to make this two more closer to one another, let's look at the low rank regression, right? So low rank basically saying this is not going to be full rank. This is W, so the W, we will make it a low rank. So that, when you are A and B, it's not like n times n, it's typically n times k. So the rank is definitely reduced. Okay. So then there is a standard way to do solving this. Okay. Then that's where we start. We say, okay, so if we can do low rank compression, regression, then let's look at how they were connected to matrix factorization. Okay, by the way, like in Stack's paper, he was able to actually, he worked on the low rank regression, for his problem, for his regularization, because adding diagonal 0 won't have the closed form solution. So that's something I will talk about later. So we are able to actually, in last year's work, the continuation of this, the first study, we are able to also derive a closed form solution for the low rank regression, but with diagonal constraints to be 0. Okay, so all of this you want to say is that this setting is low rank compression regression, but the diagonal 0 constraints is eliminated. It reduces a little bit of performance, but it still captures the essence of this approach. Okay. By the way, one thing you can get immediately is, you can think of this is the low rank regression approach. It's almost like very much similar to the matrix factorization, right? So you can think of, if you look at XA, for instance, right? So so after, if you multiply X by A, you can see that in a way it's your P, it's your like user matrix. Okay, it's actually generating, for each user, it's generating a k-dimensional vector, right? So this is, if we see, X is m times n, this is n times k. So after this, you actually getting, like m times k user matrix, right? Then your B, it corresponding to your Q, your typical item in band. So in this sense, you will say, we can easily say, oh yeah, this is, so is this is a low rank regression going to be a sort of a special form of your matrix factorization, right? Because P and Q clearly is more general. This has to be a format of X times A. Okay. Yeah. So this is kind of the problem, right? We want to say, okay, so if this is the case, how come the low rank regression approach, can they actually perform better than the matrix factorization? Okay. Yeah. So yeah, this is we want to figure out, right? There's a list of questions we want to ask. Like, so how those different approach relates to one another. Why regression-based approach actually perform better, and can we somehow unify them, compare them? And also the other thing is important because if you look at the deep learning solution, a lot of them it kind of consider is sophisticated matrix factorization or autoencoder. Okay, they were just adding more layer, but ultimately it can be their simple format come from here. So really be able to understand the difference between these two can help us actually understand the performance of deep learning models. Okay, so as I said, so this is where we boils down to this basic problem, right? Like this is the neighborhood regression-based solution, and this is the matrix factorization approach. And to make it even simpler, more specifically, we consider the following format, right? So this is, gamma, but gamma transform gamma. So this is, you can consider this is, just so-called Tikhonov regularization. It's a generalization for all the things we have been talking about, how we can regularize, like this W. Okay, so adding a generalized weight, gamma. And we want to make sure W, it has a low rank. So this is basically the simple format or the standard format of the regression-based approach, but low rank. And then for the matrix factorization approach, remember we eliminated that C because it turns out, like it's very interesting. Even though C, is clearly important, weighted, it makes it so-called weighted matrix factorization. But to make that C to be effective is actually not easy. Okay. So, I mean, in our simple experiments, we can show, by eliminating it, we can actually doing a better job in some cases. So I think there's needs more study on how you actually tune the C. Yeah. But so our matrix factorization took this basic format. So this is X minus PQ, and this is another lambda prime, and we consider P and Q for Venus norm regularization. Okay, so we want to basically from here we want to investigate, what are the closed form solution and how they relate with one another. So yeah. By the way, I want to stop for a second. Just want to see, anyone, like, is there any questions from the audience in case I, before I move forward, in case you have any questions. Okay. Okay, so like, because this is as simple as we can get, right? We implemented a lot of things, and but now the first thing we want to double check is actually if we're doing this sort of regularization, right? This simple format, can this be actually close to what we started with, right? So like it turns out, really the basic model actually capture quite a bit of essence. You can see, so let's look at the ease. Then we look at the, LRR is, we actually simplify. In LRR, in this case, it's just a lambda. It's not even this generally gamma, it's just lambda, okay, without diagonal constraints, okay. So you can see, ease clearly still perform better, under all the criteria, but LRR is not far from it, right? It's fairly close, right? It's really in the second, digits. Then throughout, it's fairly good representation. In the same time, this is kind of interesting, right? So you have WMF, we try our best to adjust it. This is also coincide with, what other people found. But it's kind of interesting, in MF solution, okay, which we just don't have that weight, but we are just, this allow us actually spending, time to actually finding a better lambda, because finding this lambda is actually difficult. So we can, try different various lambda. So you can see, the performance of this matrix factorization after you eliminate the C is actually perform better, even, better than this, like the W, the classical, WMF or ALS. Okay, slightly better, very close. Oh, so okay, yeah. So I guess one person, yeah, recall. I think this is really like just using recall, and NDCG. This is the standard, top K evaluation matrix. Yeah, you have to, if you work on recommendation, you need to know that. And this is just we look at the, basically you select the top 20, right? You see, if you see recall is basically for what's being had, you see what's the percentage of what already, what user already clicks that, among 20, how many of them are in the solution. Okay, NDCG is sort of a weighted version of that. Yeah. Okay. Yeah. Okay. Got it. Yeah. Then yeah, like K, right? It's we actually doing a great search. Like in this study, we actually tried. I think my student was actually doing a great search, try various of K and various of lambda, do a great search and getting the best performance of this. Yeah. So apparently after, after you drop that weight, like your K can become a little bit bigger, so you can get in, good results. And by the way, all of this evaluation metric, like it has little things to do, it's, we are not overfitting in a way, like, because we, during the search, we are using training data. We are not using testing data at all. Okay. Yeah. So this is sort of, it's already a, just give you a sense, this two very basic models, they were, performance is very close to the most sophisticated counterpart. Okay. So that was being published. Okay. So now let's look at what's happening, right? For those models, right? Very simple model. So the first model, this is really like, for us to find out the solution. So under this low rank solution, this is techno regularization, then, but we want the W has rank less or equal than K. So there's a, like one page kind of derivation. But one thing I probably want to say, there's a geometric insight in here. So, like what we do is, you can easily say it's like you have this Y. So in here, the Y is really like, this is the standard way dealing with this type of problem, right? You can, because they were all Frobenius normal, the L2, you can put them, the regularization together, become a simpler regression format, right? So once you have this Y bar and minus X bar, you have this rank constraints. We can decompose the problem into two parts, right? One is the standard linear regression without the rank constraints. So that's X bar multiple that W star. So W star is your, like, the ideal results, or the, for your ridge regression, that is your optimal solution you consider. But then your W, which has a rank constraint, so it won't be the same. But if you know this is just a standard regression approach, this Y is projected onto this is X bar W, it's just a projection. So end up you can actually decompose this arrow. This is what we found. We can break it into this blue part, this line, and this right. So really end up your, because you just want to optimize the right part, right? So it's really you want to find, oh, what is X bar W minus X bar W star. And that turns out you can solve it using SVD. Okay. Let's see. Yeah. So gamma is just you can consider it's like a weighted matrix. Yeah, a matrix which gamma multiple by gamma transform. It's just it can be, generally speaking, the typical case we always do it diagonal. But let me going back. So anyway, end up like so you can consider this is the gamma transform gamma in the typical case is the basic case is lambda. So gamma transform gamma, you can also have this diagonal matrix, but it can also make it like a little bit more specific. Okay, so this case you can consider this lambda. Excuse me. It's just it's just a diagonal constraints. Okay, so this is diagonal matrix, but this is really like this is just your from your SVD. So your X is become U sigma V. This is not original X, slightly different, but more or less you can consider it's just the typical like X transform X. We can call it the left singular vector. Okay, so if we pick up lambda this way, so we will have a closed form solution of W. So it has this format. So I want you to take a look. Just see, because this is quite important. So this is really like your VK is come from here, your left, your right, the singular vectors, right? It's diagonal. So original diagonal, you have the singular value, right? It's lambda 1 square. Yeah, it's lambda 1 square to lambda k square. But it was actually being scaled based on the constraints. So lambda 1 to lambda k come from here, lambda. Okay, so it will shrink a little bit. You can consider it's not the original one anymore. Okay, now for the SVD, for the matrix factorization, this is this format is actually people has actually turns out studied this before. Actually, we found a couple of papers under different contexts. They all give different name, but it's called one way is called the basic regularized SVD. Okay, so this solution has been solved. It turns out this is just different way of regularizing it. So you can see this is P, and the Q can have closed form. And if we represent the whole thing as a linear encoder, if you consider, okay, so I make XW equals PQ. So you can think of the W is simply using matrix factorization, you can getting a linear encoder format. It actually can have a very similar format of the other one. So, but this one is 1 minus lambda prime divided by sigma 1. Okay, so very interestingly, you can consider this is sort of like it's being scaled, like the ratio. The typical one, by the way, is 1. Okay, so all of them should be 1 if you don't do any regularization, right? But this is actually we actually doing this regularization. Yeah. Okay. So this is just to put these two models together, right? To look at them more carefully. So you can think of your the optimal solution X, right? Your estimator, right? If we look at PQ. So PQ, in a way, is represented in this format. So UK, sigma k. So your sigma k is where you have lambda 1, lambda 2, yeah, lambda k. Then we have this ratio, right? Like 1 minus lambda prime sigma 1. Yeah. And then the other one is just scale it differently, right? The sigma 1 square divided by sigma n square plus lambda. Okay. That's the only difference between these two. All of them actually all have the same, the rest have the same format. Okay. So now, like, and also like, in the simple case, you can see when lambda equals lambda prime, so basically there's no regularization, right? You basically return back, this is all become, yeah, like 1, right? Like, so basically you pretty much returning back to your standard SVD decomposition. Okay. Yeah, and both, from the geometric side, if you're familiar with the SVD, like how the singular value, singular vector, left singular vector, right? Then, then each of this, it's scaled by those, sigma 1 to sigma n. But in here, like kind of like those scaling factor, right? Your singular value was scaled, was shrink. Both of them are shrink, you can see, right? But they were shrinked slightly differently. Okay, so this is a constant divided by sigma 1, then sigma k. This is just adding here lambda. Yeah. Okay. Now, like, this is actually just to give you a sense on, say, why they were, how they were performing scale differently. So you can see, this is original singular value, from the like how they were. The top one, the largest one, then yeah, how they were scaled, but then their size, then after shrink, their singular value, how they change, so one thing, like you want to pay attention is, so because this is minors, right? So this part needs to be preserved positively. So when the lambda prime equals certain lambda k, right? This is lambda from the largest to the smallest, right? When you pick up certain lambda k, you can consider when you get to that point, the rest will become 0. So you can only use, so in matrix factorization, in certain sense, you can only use certain dimension. Okay, it's determined on how large your lambda. So your lambda was sort of like, it's going to cut any singular value, any dimension, if your corresponding singular value is like smaller than that, right? So then that become negative. So all of them will be cut. Okay, but this linear regression, low rank regression approach. So this is lambda. Is actually can allow you use more, right? Like you can add in a large number, but then everybody, like it can still, you can still choose them. It's not cut off. And also, like, it's would shrink the largest one faster. So if you look at this, so if you look at the ratio, you can see, like for the matrix factorization, right? So we shrink the singular value, it's like the largest one was actually shrinked smaller. Okay, so you put in a way, like after you shrink, the larger actually become larger, in certain sense. Okay, but note that is not the case for the low rank regression approach. Okay. Yeah. So yeah, like there is a list of complications there. Oh, I think I was. I think my talk is 50 minutes. Okay, so okay, let me just quickly jump. So that's actually one of the theoretical connection, right? It's really like it really boils down to how these two are connected to one another. Then like we go further. So this is sort of our new work. We kind of look more of those models. Let's see. Yeah, I can, yeah, some of the slides I can share later. Yeah. But those are actually some of the new results. It turns out, most of the linear methods we are dealing with, including some, if we simplify the deep learning approach, most of them can be basically all the things we have been looking at all can be characterized in this two regularization formats, either the nuclear norm format. This is including all the matrix factorization based approach. The interesting is, turns out, like the so-called variational encoder, right? Autoencoder, VE, but it's a linear variation autoencoder can also actually more close to the nuclear norm regularization, more close to the matrix factorization, right? Then the other is like the Frobenius norm regularization, like EDL, AE, IRR, like all the other things. Yeah. So like I have to go through this quickly, like if you're interested, I can share the paper. So we basically, can categorize them, the short message is, and there's something even more interesting is what we found out, like if we doing the so-called linear variational autoencoder, right? We will be able to come up with a new generalization format, something like this, which hasn't been studied before. Like this is, you look at this X minus XAB, this is like, oh, very similar to the low rank regression, right? But the regularization is like XA of this part plus gamma B. You can think of this gamma as a diagonal matrix, okay? Like, so, does this one can have a closed form solution, right? Like, so we found out, yeah, it is. And there's something even more interesting. So what we found out, this problem is actually equivalent to this problem. It's actually, yeah, like equivalent to the matrix factorization problem we have looking at, but it's a generalization of the matrix factorization, right? In matrix factorization, we typically have the lambda. But what if we put the gamma? We like each of the dimension, we give different constraints. So we have weighted constraints, right? Lambda 1 to lambda n, lambda k. But what's interesting is, this is quite surprising when we found it. So if you have this way, right, you try to solve it. So there's sort of like this auto reorder happening. So always your singular value, your largest singular value, always going to be reduced by the least singular value, least regularization factor. So like this is always going to pick up the smallest one. So basically you can consider in matrix factorization, if you do a weighted version, if you have the largest singular value, like richer still be richer, even though it's reduced. So like your largest factor is still be larger. It's even become larger. Okay. So, and that, turns out, this is not a good thing actually for recommendation. Okay. So this is, if you do that, we found actually, if you're doing this generally weight, so typically this is actually will getting worse results. This is also how coincides with what why the linear, the low rank regression, right, is actually more effective because it actually shrink. It makes the larger one become a smaller. So it's kind of like getting all the singular values closer to one another. But in matrix factorization, and it apparently also for like this generalized, like a linear variational autoencoder, this is, you have this very interesting auto sorting mechanism. It's always built in. Okay, so we feel that's partially could be a inherent limitation for matrix factorization approach, because even you want to shrink them slightly differently, you cannot. It's not easy to do. Then the other thing also very interesting is like if you put a p here, this can be any arbitrary number. It turns out the result's going to be the same. So no matter it's L1 or L2 regularization, it won't be able to affect the results. By the way, this is the nuclear norm representation. Okay. Yeah. Yeah. So then just quickly like we also go ahead to solve a so-called full rank EDLAE solution. Before it's only have like ADMM solution. it just, like it doesn't have a closed form solution, but we are able to propose based on what we've done, propose 2 closed form solutions for that. It turns out the results, like it's actually perform even better than the, ADM, this approximation, iterative approximation solution. Okay. Yeah. So do I have a couple of minutes? So I should stop because I think this is sort of the first part of the talk, really.
I think maybe we try to wrap up
Yeah.
because I think many people will have schedules in
Okay.
meeting schedules. So
yeah. Okay. Yeah, I think that's really like the other part of the problem. We can share our paper. It's really like it's just one message I want to give is when you're trying to use item-based sampling. So when you do the top K, right, evaluation, right, because your item, if your item is too large, have 1 million, 10 million items, then if you want to sample a list of items, right, to evaluate top K, then you have to be really careful. Yeah, because the solution you get is not necessarily directly correlated with if you look at the entire one. If you look at, let's say you pick up 1,000 items to do top K, comparing with you do 1 million, the entire collection, right? The results will be very different. So this involve a rather sophisticated estimation problem, right? How you can get in from the sampling result, can you use that to recover the global results? Yeah. Okay, so yeah, with that, I think I will stop. Like this is. Thank you. Yeah, it's also, this is the joint work with my PhD student, my collaborator from William Mary, and a couple of collaborators from iLambda. Okay.
Thanks a lot for Professor Jin and his time. I think it's great, and I think we have question in the audience, but whether the slides will be shared. So I know this talk is being recorded, and this will be uploaded to YouTube later. But for the slides, I don't know what it's. I think it's completely in Professor Jin's.
I think I can share with you later. Yeah, some of summary. Basically some of the results are actually under submission, under review. So yeah.
I see.
Yeah, so if you keep it private, like probably even for YouTube, maybe keep it for a while.
Okay. Yeah. So then I think for now, let's just not share the slides, and I think for the information people can get probably from the YouTube, from the recording from YouTube. But if anyone who is interested in the slides, I think maybe you can email Professor Jin directly. Yeah. I think the information should be in the invite. Yeah, so that probably will be the easiest thing to do.
Yeah.
Okay. Yeah, so if we don't, do we have any
I think there's a couple more questions I can address.
Yeah, so if you can go through the questions.
Like it's the intuition of sorting. Yeah, it's really, when we discover that, we really also feel quite, it's a pessimistic result in a way, right? It's kind of, initially we thought, after, if you give the lambda, right? Like it's a constant lambda, now we put more on the diagonal, right? This is more power. But it turns out, it's always going to somehow, right? After the optimization is done. So basically your largest singular value always going to reduce by that smallest diagonal constraints you put on. Okay, so there's a very rather sophisticated, like optimization happening there. So you can consider, in order for this, for our results to be optimized, there's auto rotation kind of automatically happening. So that's kind of like quite a bit of surprise. Yeah. So in that case, yeah, it's always like no matter how you like assign your diagonal constraints, right? For your like lambda, right? For P and Q, okay, it's always going to be the same results, sort of, yeah. And then the other question, if we distinguish now and 0 can we still use a matrix factorization approach? I guess it's what you mean now is 0, meaning you know they are negative results. Right now it's just unknown, right? Yeah, this is really like, I think that this is, you know, I would say one of the also key problem for the recommendation. I mean, through the various experiments, you know, so far like 0, keep at 0. We also try different ways to play around, but so far like everything, you know, like negative and not known to be 0 seems to be a valid solution. You know, it gives reasonable results. We haven't found any good ways actually to solve it. But one highlight I want to tell is you can try, this is something we found, like if you know like it's negative, right? It's like it's so basically if you record the we call impression, right? Basically how many times a user have looked at the item, okay, then how many times they click, for instance, then that data can be somehow utilized. I put this way, right? It can be utilized in a very smart way, so you can get better results. Yeah. So it's so basically, you know, all this does not necessarily has to be binary matrix, but binary matrix is just the way right now for implicit we typically assume that.
Okay, if we don't have any more questions, let's thank Professor Jin again for this great talk. And also thanks everyone for the time to joining. And as mentioned, the recording will be available. We'll post it on YouTube soon. And also if you have questions, feel free, I will just take the liberty to say, feel free to email Professor Jin, and also if you want to the slides.
Thank you. Yeah.
Thanks everyone. See you next time. Bye.